Today's topic is the Claisen condensation, which is the ester analog of the alcohol condensation, as well as the variations on the Claisen condensation, such as the mixed or cross-Claisen concentration, and the cyclic analog, which is known separately as the Diekmann condensation. So let's start with basic Claisen condensation. Which we saw in the previous video is the reaction of ester, like methylpropanoate, with itself in the presence of a base that is the conjugate base of the same alcohol that ester is here. So we have a methyl ester. We're going to use methoxide ion to avoid transesterification. If this methoxide group reacts with the carbonyl carbon, instead of removing an alkyl hydrogen, it simply displaces an identical methyl group, and we don't get any change. And as usual, when we use sodium methoxide, we typically use the conjugate acid methanol as the solvent again, so that if it takes off this proton, we just generate methoxide again, and there's no net change. I'm going to write out this alpha hydrogen explicitly because the first step in this mechanism is going to be to remove the alpha hydrogen using the base. And we know that the pKa of this hydrogen is around 25. So significantly less acidic than the ketone or aldehyde hydrogen, which means that the equilibrium is going to be quite unfavorable. Yes, I can show that. The equilibrium arrows show only a small amount going in the forward direction. And we have a resonance stabilized anion which has significant negative charge on the alpha carbon. The more stable being the kind of ester enolate. And the equilibrium constant being approximately 10 to the minus 10, because the pKa of methanol, the product, is only about 15, and the pKa of the hydrogen is just removed is 25. So it doesn't happen very often. There's not much ester enolate in solution, but to the extent that there is ester enolate in solution, it can now react to form a new carbon-carbon bond as this pi bond is pushed into attacking the carbonyl of another molecule of methylpropanoate. So step one is decarbonation to form enolate. In this case, the ester enolate. And step two is the nucleophilic addition, which is exactly what we would have expected if that was a ketone or aldehyde carbonyl. The first two steps are fundamentally not different from what the first two steps would be for the alcohol condensation. But it's in the third step that we're actually going to have a different reaction. So we now have a new carbon-carbon bond. And we have negatively charged intermediates or neutral intermediates because we're in basic solution. If this were the alcohol condensation, the next step would have been to protonate this oxygen to generate the beta-hydroxy ketone. But instead of protonating that oxygen to generate the beta-hydroxy ester, in this case, we're going to use the fact that we have a leaving group attached to the carbon. So instead of doing a nucleophilic acyl addition reaction, we do a nucleophilic acyl substitution reaction. condensation in step 2, and elimination of the leaving group in step 3. To regenerate the ketone. And generate the beta-ketoester. You'll notice that I've written all of these steps as equilibria. This reaction is reversible. The reverse reaction would be called the retro-Claisen reaction. What drives the reaction forward is the fact that we still have an acidic hydrogen, and now that that hydrogen is sandwiched between an ester carbonyl and a ketone carbonyl, the pKa is approximately 11, which is significantly more acidic than the pKa at 25 when it was next to OB1 carbon oxygen double bond. In fact, being sandwiched between two carbonyl groups lowers the pKa dramatically, as does being sandwiched between two carbon-nitrogen triple bonds. The pKa of both of these is approximately 9. Being sandwiched between one ketone carbonyl and another ester carbonyl, with a pKa of roughly 11. Being sandwiched between a nitrile and a ketone carbonyl gives it a similar pKa as being sandwiched between two ketones of about 9. Being sandwiched between two esters produces a pKa of about 13, which is around the same as being sandwiched between two nitriles. And the reason for that should be obvious, because now there's resonance stabilization in both directions. So we can have two resonance structures that put negative charges on oxygen and just one percent on carbon, with a resonance structure with negative on oxygen and nitrogen, or two oxygens in these cases, or two nitrogens in these cases. So all of these are more acidic than the alcohol, which means that the equilibrium for this deprotonation. And you could ask yourselves the question, which carbonyl will it resonate with most favorably? And the answer to that is the ketone carbonyl. There's more partial positive on the ketone carbonyl carbon than there is on the ester carbonyl carbon, because remember, there's significant contribution from a resonance structure that has the carbon-oxygen double bond to the ester oxygen because of good orbital overlap. And the equilibrium constant for this reaction is now about 10 to the 4th, because we have a difference between a pKa of 15 and a pKa of 11. So the equilibrium lies strongly to the right. Significantly resonance stabilized anion and to drive the equilibrium forward. It's important from the perspective of driving this equilibrium forward to have that second alpha hydrogen available. Therefore, in the absence of a second alpha hydrogen, stabilize the left. And a reverse or retro-Claisen condensation occurs. So if you have made a beta-ketoester, it has no hydrogen on that carbon between the two, right? We now have no acidic hydrogen to remove. And since I've done an ethyl ester here, we would use ethoxide as our base. The more likely carbonyl for it to attack, that's the larger delta positive, is the one that's not stabilized by resonance to the other oxygen. So most likely carbonyl to be attacked is that ketone carbonyl. You'll recognize that this is the reverse of step 3, where we had the leaving group leaving, being kicked out. We're now attacking that ketone carbonyl. And then it can reverse and kick ethoxide right back off, but it can also kick out this ester phenolate, which you'll recognize as the reverse of step 2 of the forward Claisen reaction that we just did, Claisen condensation rather. And this is a nucleophilic acyl substitution reaction as well. One of the products here will be the ethyl propanoate, and the other product will be the phenolate ion, which will then pick up a proton from ethanol. Reforming the other ester. And giving us ethyl 2-methylpropanoate as the other product. So we've taken the beta-ketoester here and created from it 2 separate esters, both ethyl esters, since we used ethoxide as the leaving group. So the reverse Claisen reaction is favorable in the absence of that alpha hydrogen that drives the forward Claisen reaction towards completion. If we were to try to do a Claisen condensation with 2-methyl or ethyl 2-methylpropanoate, the reaction would likely fail because condensing this with itself would generate a product that has 2 methyl groups in the position between the two carbonyls and thus no ability to drive the reaction forward. So the question might arise, is it ever possible to do a forward-Claisen reaction with two different esters such that you would generate a single product rather than a mixture of products? That'll be the subject of the next video.